Hello students, this is a video about week 4 notes for MAT120 elementary statistics. We're going to be talking about linear regression, and there are quite a lot of slides in this, so I'm going to try to go through a little bit quickly. Hopefully you will be able to catch what I'm laying down. The first slide talks about linear regression and correlation. Here are the questions that we're going to try to answer. How are trends identified in data? What exactly is linear regression? Why is it called regression? And how do we determine and measure correlation? And these are the objectives. They're very similar to the questions that you just saw. On this first slide with content on it, you can see that there is a scatter plot. We define a scatter plot as points that are just scattered onto an X and Y axis. This is data about the speed of a toy car at the base of a ramp, that's speed down here, and then the distance it travels, that's distance on the Y-axis here. Speed is on the X-axis, we call that independent or explanatory variable, and distance is on the Y-axis, that's the dependent variable or the response variable. We say that this variable explains this variable's response. That's where explanatory and response come from. Here's another example of bivariate data. It's height and weight in general. As somebody's height increases, their weight generally necessarily increases, not always. All right, on the next slide here, we talk about association between two variables. Before jumping into the idea of correlation, let's talk about association. Two variables are associated if they tend to vary at the same time or in the same way. It doesn't have to be the same way, but they are usually varying at the same time. Correlation is when one of them is related to the other in some way, when you can prove that one of them is increasing at the same time the other is increasing, or vice versa, one of them is increasing when the other is decreasing. We usually look at correlations using graphical assessments. In other words, we graph the scatter plot and we try to figure out whether it looks like a line or not. We can also use a numerical measure of linear association. That answers the question how we can determine whether two variables are correlated. We're going to be looking at that at the end of the slideshow. A scatter plot is a graph, as I said before, in which there's an X and a Y. Each of these individual points is a piece of data. It's two pieces of data. For example, this individual red point represents a speed of about 24 and a distance of about 125 or 130, right? This point has two different variables attached to it, the X variable and the Y variable. Looks like a bag of M&Ms which is scattered onto the graph. That's why we call it a scatter plot. What a cute name. Positive correlation is where both variables increase. So you can see that basically all of the variables are increasing within these two arrowed lines here. It doesn't look like it's very perfect. It doesn't look like they all form like one perfect straight line. However, it looks like in general they're increasing. And you can draw two lines on the outside, or more typically, people will usually draw one line that's in the middle, and we usually call this a trend line. And the trend line is trying to get as close to the points as possible. It goes through the data cloud. Another example of positive correlation is a stronger positive correlation. You could draw a trend line through here in the middle, and you can see that the two other arrows are kind of closer together, right? This was a positive correlation, which was a little bit weaker, whereas this one is stronger because the points are closer to the line. And this we call a positive correlation that is perfect. If we take an arrowed line and we draw it here, it looks like it hits every single data point. So we call that a perfect positive correlation. We can do the same thing for negative correlation. These two arrows are going downwards at the same rate, and it looks like all the points are in between those two arrows. Then we contrast that with a stronger negative correlation where the arrows are closer together or the points are closer to the arrows. Respectively, we can still draw our trend line from before like this. And then the strongest negative correlation is called a perfect negative correlation, where we take our trend line and we draw it and it just hits every single point exactly. This is a perfect negative correlation in which all the points are basically on the line. This is a non-linear correlation or no linear correlation. It should look familiar. It's a parabola, like a quadratic equations graph. You don't have to create models with quadratic equations in this class, although the TI-84 and similar calculators will let you do it. All you need to do is identify situations that are nonlinear. So for example, if I give you a group of data and I say, plot this on a scatter plot and tell me whether it's linear or nonlinear, you have to look at this and be like, Mr. Scordine, it's nonlinear. Moving on to the next type of nonlinear, this is an interesting type of graph. It looks either like a sinusoidal function, you know, the sine function that goes up and down like a sound wave, or a cubic function because it has that concavity change here and another concavity change here. It could look like one of those graphs, like a cubic graph that goes down, up, and then down again, and then it goes to infinity both ways. Again, you don't have to fit a graph to this. You don't have to fit an equation to this. You just have to identify that it's nonlinear. Moving on to the idea of scatterplots. A scatterplot helps us answer this question. How strongly is the data correlated? In other words, how much does this data look like a perfectly straight line? And what we're going to be doing is using the linear correlation coefficient to numerically estimate that correlation. In previous problems, in the previous pictures, you could see that, for example, this one is a very good correlation. This one is not a very good correlation, and this one is kind of in the middle. So instead of saying the things like, well, it's kind of good or in the middle, we're going to use a numerical value for that. This is Carl Pearson. He believed that statistics was the grammar of science, and I believe that he is correct, so we both believe that. The linear correlation coefficient measures the strength of the association between x and y. We're not going to be using this symbol in this class. This is the Greek letter rho. It kind of looks like a P, but trust me, it's rho. We're going to be using R, which is a statistic. We're going to be looking at data and trying to figure out how well that data, that statistical data, from a sample fits an idealized version of that data. In other words, fits the average of those data. So how do we calculate R? You don't have to do it. It's on the calculator. But if you ever wanted to do it, if you ever stuck on a desert island and you wanted to find the correlation coefficient of some data, like you were looking at how often the sea turtles come to your island or something like that, you would use this formula. This top part just talks about the difference between each x value and the average x value, the difference between each y value and the average y value. And on the bottom here, it gives the standard deviation of x. You can tell that it's a standard deviation because we're taking the deviations and we're squaring them and we're adding them together and then we're square rooting them. So that's basically what standard deviation is. And this is the standard deviation of, I shouldn't say x here, I should say y. All right, I'm going to fix that right now. Oh, wow, it's already fixed. Amazing. X bar is the mean of the x variable and y bar is the mean of the y variable. That just explains this formula. However, you will be able to calculate this on your calculator. No worries on that. For the correlation coefficient, the value of R is always between -1 and 1 inclusive. That means that R is always between -1 and 1, and it can be -1 and it can be 1. That value of R doesn't change if either variable is converted to a different scale. For example, if you're doing degrees Fahrenheit and then you change to degrees Celsius, the value of R does not change. It is resistant to change in that way. And it's not affected by the choice of x and y. If you change your explanatory and response variables, it still gives you the same R value. So that means sometimes a scientist will measure two variables and they'll think, well, what if this one affects this one? Or like, what if this one changes this one? It doesn't really matter in their analysis which one is the explanatory and which one is the response, because it just analyzes how closely they vary with each other. It's only used for linear associations, not nonlinear associations, so we can't use it for that crazy situation that we saw before, this sinusoidal curve or this cubic curve. We can't use it for that, but that's okay. I would never ask you to do that. That's irresponsible. Let's see. Here's the correlation coefficient in terms of a scale here. You can see I used emojis because I'm talking to the children of America. These emojis indicate this is a weak correlation. These are strong correlations. And you can see that as it goes away from 0, if it gets farther and farther towards +1, or if it gets farther and farther towards -1, those are considered stronger correlations. And the weakest correlation is the correlation with a value of 0. In other words, there is no correlation between the two variables. Let's take a look at how the R value looks on a couple of graphs. So if I'm looking at all of these different graphs, you can pause the video and take this in if you'd like. If I'm looking at all of these different graphs, you can tell that these ones have positive correlations. They both have all three of them have trends that are going upwards. These are negative correlations. This one is no correlation because it's going to be very difficult to draw a line through this in any way, shape, or form. You could draw it here, but these points are very far away. These points are very far away. This is another nonlinear correlation like we saw before. And this is more like that sinusoidal or that cubic function. So now you are able to identify the different types of correlation. Now let's put some numbers to it. Keep in mind that all of these are different types of correlations, so they should all have different numbers. For this situation, all of these positive correlations, this one, and this one, are positive values, right? Positive R values. This one is 1 because it's a very perfect, strong correlation. This one is 0.93 because it's pretty close to a straight line, pretty close to a perfect line, but there is some variation. And this 0.58 is a little bit farther away from a tight correlation, so it does have a lower value. It's closer towards 0. The same thing is going on here. All of these negative correlations have negative R values. This one's -1 because it's a perfectly straight, negatively sloped line. This is -0.88 because it's going downwards, but it does have that little cloudiness to it. It does have that variation to it. And another negative correlation that's a little bit weaker. This correlation coefficient is 0.05. It's very, very close to 0. That's because there's no correlation here. In general, we could say that if it's very close to 0 in this way, if it's in the single digits in terms of percentage points, or if it's in the hundredths place only, you could say that it's probably going to be no correlation. Here's another no correlation because remember R is talking about linear correlation. This is no correlation because there's no linear correlation. However, if we were measuring the another value, whether we're talking about the correlation of a nonlinear value, then it might be a little bit different. But again, R only measures linear correlation. Same thing here. It only measures linear correlation, and there's no straight line here. It's one of the ways that we can evaluate the spread of the data. We can say, well, how is the data spread out? It's spread out in this way. It's spread out in this way. That's what R seeks to answer. Here's another set of examples. They're perfect positive correlation to perfect negative correlation and everything in between. Remember, no correlation is just going to be scattered all over the place. It's going to look like there's no trend, and for good reason. No correlation means no trend. Here's some other examples of correlation coefficient in action. All of these are correlation coefficients. This is R equals -1. This is R equals -0.8, etc. Another thing that you should keep in mind is that the correlation coefficient is not the same as the slope. For example, this is a correlation coefficient of 1. So is this, even though it's a different slope, because we're not talking about how it's sloped. We're talking about its increase over time and its tightness of fit, its goodness of fit. Another perfect 1, and this one doesn't have a correlation because it's not increasing and it's not decreasing. But again, -1, -1, -1, all the same, and all of these should be 0 correlations because they do look like they have patterns, but they are not linear patterns. One thing that I have to keep in mind and that I have to tell you is that correlation does not imply causation. In other words, we can't say that two variables are correlated, therefore this one causes this one. We can just say that there's a relationship. Then once we can say that there is a relationship, we can further study them, and maybe we can have a medical researcher or an environmentalist do something like that. A statistician's job is just to say there is a relationship, not that one of them causes the other one. So correlation, not causation. Here's an example of correlation not implying causation. As the global average temperature increases, the number of pirates increases. Oh, wow. So that means the number of pirates causes the global average temperature to increase. Obviously, that's very silly. Here's another very silly one. People who drowned after falling out of a fishing boat. As that number went down, the marriage rate in Kentucky also went down. But even though these are correlated, they happen at the same time, they have a relationship, that doesn't mean that more people, or fewer people rather, falling out of fishing boats causes more people to get married in Kentucky, because that's spurious. That's very silly. Another one is deaths caused by lightning as compared to per capita consumption of beef in the United States. Obviously, that's not going to make any sense at all. These are some interesting examples of where correlation does not imply causation. Moving on, oh, hey, algebra, I remember you. We should be able to represent the equation of one of these lines in y equals mx plus b form. The regression for the car data, the data from previously, you can see that this straight line intersects the y-axis at about -5, and it's got a rise of 20 and a run of 5, so 20 divided by 5 is 4. So we're able to write the equation of the trend line like that. We're using slope and y-intercept. Moving forward here, sometimes you'll look at a graph to find the y equals mx plus b, the line of best fit, and sometimes you'll be using a calculator for that. Here is a regression equation in which we do y equals b plus mx. It doesn't matter which way it is oriented, it just matters which one has the x variable on it and which one is the constant. All right, we should be able to use regression equations for predictions if there's a significant linear correlation. So if you look at it and the correlation coefficient is like 0.7 or 0.8, you should use the regression equation. If it's too low, though, if it's a weak correlation, we should not use the line of best fit. In this case, we can see the red line is better than the black line because the line of best fit is supposed to be the closest to as many points as possible, and the red line accomplishes that task. Residual is the distance between the points and the line, and If there's no significant linear correlation, you should not use the equation to make predictions. All right, this was a video on week 4 looking at linear regressions in MAT120. Good luck studying.